Hello, I'm Christopher Berry. Unusually for the LISA Symposium, I'm going to talk about a mission other than LISA, specifically a Decihertz gravitational wave detector mission to come after LISA. I'm going to present a body of work put together by a study team where we submitted work to ESA for the Voyage 2050 mission call to look at missions on the 2030 to 2050 timescale. Now, we all know that LISA is wonderful. However, it only can access a part of the gravitational wave spectrum. Here is a plot showing the main bands we currently have designs on observing with gravitational wave detectors. We have the ground-based high-frequency gravitational wave detectors, LIGO, Virgo, CAGRA. In the middle, we have the millihertz range, which of course LISA will probe. And at low frequencies, we have pulsar timing, the various pulsar timing arrays. We have a wide range of different frequencies covered, each of which gives us access to different types of sources. In particular, if we're looking at mergers of binaries, the mass of the binary is inversely proportional to the frequency. So the more massive an object is, the lower frequency it merges at. So the ground-based detectors are perfect for stellar mass objects, stellar mass black holes, neutron stars. LISA is perfect for massive black holes from the center of galaxies, 10 to the 5, 10 to the 6 solar masses, whereas pulsar timing goes for the supermassive black holes, the really massive merging black holes. So putting these together, we have a good coverage of the gravitational wave spectrum. However, there are still gaps. And in these gaps might be exciting new phenomena which we are missing out on. And we will be focusing on this decihertz range between LISA and the ground-based detectors. We need a space-based detector to observe this range, as there's too much seismic noise on Earth. So we will be looking at the potential here. Now, we put together this white paper for the ESA call, and we examined the science case for this range. Now, looking at the Decihertz range is not a new idea. There are a wide range of missions which have been suggested for this. Perhaps the most familiar would be ALIA, which is a heliocentric, similar to LISA mission. There's also Tianjin, Tiaji, Decigo, Tiango, which is a combination of Tianjin and Decigo, which are all similar concepts or familiar configurations to LISA. Decigo is slightly more complicated. It has resonant arms similar to LIGO rather than the configuration used in LISA. There's also some slightly less ambitious missions using on a tighter budget, Gadfly, GLISA, SAGE. There are missions which are using new technology of atom interferometry as opposed to our familiar laser interferometry, which are Magus and EDGE, I think that is pronounced. And finally, Big Bang Observer is perhaps the most ambitious, which is really 4 copies of LISA, 2 overlapping each other in a sort of hexagon configuration, and then 2 extra constellations filling out the orbit. So you have sort of 3 equally spaced constellations orbiting around the sun. In our white paper, we didn't want to pick an existing mission as a straw man concept, as obviously there are connotations on which science agency prefers which design. So we adopted 2 fiducial models, a conservative and optimal design, to kind of bracket what we could do with a Decihertz detector. Now, there are many detectors here. That's not necessarily a bad thing. And there was, in fact, a second white paper which looked at high angular resolution gravitational wave astronomy and specifically considered the case of what if you had multiple Decihertz detectors, then you can get a much better localization on the source. I won't go into the science of that white paper here, but there is more science than I will cover here if we have more detectors. So here's a quick overview of the sensitivity of the different detectors considered, or a few of them at least, and some comparison to some of the sources we're going to have, so you can see how these noise curves fit between the current ground-based and space-based missions. Okay, so I promised that there would be dragons in this region, or at least the promise of them. So I'm going to consider 3 potential dragons, which are highlights of the science case we investigated. Those are stellar mass binaries, intermediate mass black holes, and fundamental physics. And as we go through the list, we're going to go from the most concrete scientific case to the most speculative, so that going from low risk to high risk, and the greatest rewards for the discoveries for something new there. So starting off with the stellar mass binaries, we know that these are a gravitational wave source. We've observed them with LIGO and Virgo. Soon after the first detection with LIGO, it was pointed out that the systems observed by LIGO could have been seen by LISA, ELISA as it was then, a few years beforehand. And this revitalized the idea of multiband gravitational wave astronomy. This is where you can either observe the same source in multiple bands, so it evolves from one band to the other. So it starts off wide binary at low frequencies, it will inspiral together up to high frequencies and eventually merge. Or if we don't see the same object, we can still see the same population, and by combining information we have on population seen at different points, we can get better constraints. This type of multiband astronomy can reveal a lot about the formation mechanisms of these sources, as well as provide improved measurements of parameters. If we get the single source going through, we can also predict merger times, which is particularly handy, not so much for the black holes, but if we had, say, a binary neutron star where we expect an electromagnetic counterpart. So this is incredibly rich science. However, the issue is the range that we can see these sources out with LISA. So here's a plot showing the horizon redshift for equal mass binaries as a function of mass here. And you can see for a 30 plus 30 solar mass binary, similar to what is often observed by LIGO and Virgo, LISA can see out not to even a redshift of 0.1. So it can only see really nearby sources. So it could maybe see GW 150914, which was the first LIGO detection. However, if we consider that LISA will be flying in the 2030s, we're by then on track to have 3rd generation gravitational wave detectors like Cosmic Explorer or the Einstein telescope, as shown on this plot. And you can see for 30 plus 30 solar mass binaries, we're going to see all the way out past redshift 20 with this detector. So in effect, we're going to see all the binary black hole mergers in the universe. We're going to see thousands per year. So comparing this, the fractional gain we will have from a handful, potentially, of multiband observations with LISA is comparatively small. It's not going to give us large number of statistics. It will only be a few sources that we can capture. However, with a Decihertz Observatory, you can see that we can basically match the range of the Einstein telescope here, get out to, well, redshift of a few, out to 10 at least. So we'll be able to see a large fraction of the same sources. We're going to be able to see them over an interesting period of the universe, out to the peak of star formation history, see how the population evolves. So we'll really be able to do comparable multiband observing. And if we shift now to look at the lower masses, if we go down to 1.4 plus 1.4 binary neutron star, you can see the prospects for observing one of these with LISA is negligible. But with Decihertz, we can still get out to a redshift of 0.1 or so. So we could catch the nearby sources, which are, of course, the most exciting for electromagnetic observations. This plot goes down to very low masses of a 10th solar mass. This plot is made for point particles, so these results would be appropriate if primordial black holes exist. For lighter stellar remnants, so white dwarfs, those would actually merge at a higher frequency, so there's no prospect of them being observable by ground-based detectors, but we could still catch them with Decihertz observatories. So that might be exciting for type 1a supernova, which may come from white dwarf plus white dwarf binaries. One of the things we can learn from these multiband observations of binary black holes is their eccentricity. Eccentricity is a key indicator of formation mechanism. In particular, dynamical formation channels have very particular predictions for eccentricity. This is what is shown here. However, as the binary inspirals, it radiates away its eccentricity to become much more circular. So by the time you get down to the highest gravitational wave frequencies, your eccentricity is tiny. So we have very little chance of measuring it with ground-based detectors. However, if we observe earlier, as is possible with the Decihertz gravitational wave detector, we will be able to measure the eccentricity, get some ideas of the formation mechanism. And if you look at the 0.1 Hertz results here, you can see two different populations for binaries formed in globular clusters. And you can see that the eccentricity distribution is different for binaries which are ejected from the cluster versus those that merge in the cluster. So it's not just being able to distinguish dynamically formed binaries from those, say, formed in isolated stellar evolution, but we can tell different channels within the dynamical formation apart. So we get more information on these black holes, understand the population, understand how they form. The second dragon I talked about was intermediate mass black holes. So these are black holes between the stellar mass black holes formed from collapsing stars and massive black holes in the center of galaxies. So 100 solar masses up to 10 to the 4 solar masses or so. From this plot again, you can see that this is really the peak of sensitivity for our Decihertz detectors. This is the range where these black holes merge. It's where we get the loudest signals. We don't yet have good evidence for the existence of intermediate mass black holes. We don't know what mass range here is populated, if there is a break between the stellar mass black holes and the more massive black holes, if it's a continuum. Here, with Decihertz detectors, we'll be able to do a complete survey for intermediate mass black hole binaries out across the history of the universe and see if this population exists and how it evolves if it does. As well as considering intermediate mass black hole plus intermediate mass black hole binaries, we can also consider intermediate mass ratio inspirals, where we have one intermediate mass black hole and then a stellar mass black object. So here are predictions using a particular model explained in the paper of expected rates of intermediate mass ratio inspirals with different companions. See, LISA is not well adapted for this. It's for heavier systems. So the prospects of seeing an intermediate mass ratio inspiral is very low here. With the Decihertz detectors, we can observe out to a considerable redshift and get at least a handful of these systems. So we'll be able to, again, identify if these systems exist and get some ideas of the population. And this will be particularly informative for telling us about the dynamics in environments like globular clusters, where these intermediate mass black holes are predicted to reside. So that's two dragons. Getting now to the third and most speculative of fundamental physics. So there are multiple things we can do in terms of testing our understanding of general relativity, understanding our standard model of particle physics in the Decihertz range. So I've highlighted three particular tests here. The first is that we can test gravity in a new frequency range. So gravitational waves are a wonderful way to test gravity, black hole mergers particularly. We have highly dynamic space-time. We have very strong gravitational fields. The Decihertz range has not been tested, so if there's any phenomena which happens in this range, we would miss it unless we have a detector here. Furthermore, the multiband observations allows us to combine observations of an inspiral over a very long baseline, and this allows us to very precisely measure the evolution of the phase of a binary as it goes from quite wide to merger. So putting these pieces together, we can do extremely precise tests of general relativity. So that's the first point. The second point is we can search for particles beyond the standard model. So in some scenarios, we can have resonance scattering, super-radiant scattering off a rotating black hole. So we have something like a bosonic condensate, perhaps for some of the models for axions, have this forming around a black hole. It resonantly scatters off this, it gets amplified, sometimes known as the black hole bomb. And we can measure a coherent gravitational wave signal from this. The mass of the particle we are sensitive to is set by the mass of the black hole. So if the size of the orbit is comparable to the de Broglie wavelength, we will see something. So the mass range of the particles is set by the mass of black holes. So in the Decihertz range, where we're most sensitive to intermediate mass black holes, that works out to 10 to the minus 14 electron volts. Again, it's a very unique signature of the Decihertz range. We will be able to probe this, perhaps find some exciting new axionic particles here. Finally, we will be able to probe the stochastic background. Here on the plots here, I show integrated parallel sensitivities to the background. Each frequency range of the background gives you an insight into different phenomena which could have caused this background. So in the Decihertz range, we can probe phase transitions in the early universe occurring at energy scales of 10 gigaelectron volts up to a few tera electron volts, which is, again, an unexplored region. One of the things we could potentially test is a background from cosmic strings. And the cosmic string tensions we could potentially get out down to 10 to the minus 19. So new physics, we're not sure if we would see any of this, but if we do, of course, it would be incredibly exciting. To recap, the Decihertz gravitational wave spectrum is waiting to be explored. There are new sources which we know we will find in this range. We'll be able to see the multiband stellar mass binaries out into the early universe. We'll be able to have warning for multi-messenger sources. We'll be able to get information on the formation of these binaries. There are also sources potentially to be discovered in this range. The Decihertz range is perfect for intermediate mass black holes, and by observing these, we'll be able to really see where these systems came from. Finally, there are the most speculative potential sources in the Decihertz range. We have new tests of general relativity, we have new tests of particle physics and early universe phenomena out there. Only can we discover these with a Decihertz gravitational wave detector, so we do need missions after LISA in space looking for gravitational waves. Thank you very much.